want to just get back to the sequence model. So we started to talk about, so last time after finishing up with the CNN, we talked about this fact that in practice, most cool applications of AI that you deal with, they all contain sequence data. And the sequence data has this specific property. The entries inside the sequence are temporally correlated. So it means that, for instance, if you are thinking about an audio or an image, a text or a video, every single frame that this data is somehow related to the other frames, right? This image in the video relates to the one before and to the one after, right? So it cannot be one frame and a totally different frame afterwards, because a video of similar frames just moving slightly, right? So this kind of property gives us an indication that we really need to process sequence data, right? And if you think about the kind of problem that we thought up to this point, it was actually a simple one-to-one problem. Like your data is one object. It could be image. It could be a set of features or whatever. The output is one object. It could be the class. It could be another image, or so on. But in practice, we could have different types of problem when it comes to the sequences, right? We could have one-to-many. We talked about this. This is like image captioning, right? One image goes in. A caption, which is a text, a sequence of data, comes out, right? You could have many-to-one. So you can have a sequence of data, like a text, and it's going to convert into one image, right? Just ask the neural network to give you image with these properties, right? You could have many-to-many problem this type, which means that you give your input, and then your output starts somehow at some point, and it goes on, but the output is not of the same length as the input. Famous example is the translation, right? You give a sentence in one language. You want to translate it into another language. Probably you need to wait towards the end of the sentence, so you do not start right away to put the output sequence, and the output sequence does not need to be of the same length, right? One long sentence in one language could be very short in another, right? So this is many-to-many type 1. The other one is many-to-many, where you have one-to-one connection between every single input and output. For instance, word indexing, like you have different words inside a sentence, and every single word inside that sentence has a role inside the sentence, right? And you can give label to every single one, but again, it's a sequence, right? Because one particular word, like apple, depending on where it shows up in the sentence, it could be a subject or an object inside the sentence, right? So the output also uses the temporal correlation between samples, right? Between the entries inside data. And it could be also some sort of totally non-aligned input and output sequence. You have a text, and then you want to say, this is the first sentence, this is the second sentence, and so on. So you're going to give an output once upon a time, and this is when the sentence is over, right? So there's no need that they be totally aligned. Now, what we want to do today, we want to just take a look at basic models, basic sequence model. I'm going to just give you a hint or an overview on how RNN would work. I give you some examples of famous RNNs like LSTM and GRU, but I would not get into details. You could check it out. I mean, it's not a very complicated thing, but they are not very practical anymore. And then we're going to get the idea how we can launch from there towards transformers. And then once we get there, we already get in the idea of language model. Like we can generate a text. And then we try to somehow extend this idea to generating more complicated kind of data. And then this is basically what we cover in generative models. OK, let me start with the idea of recurrence. So if I have a simple neural network, this neural network is going to take one input, right? Here, x is the input. Probably it has a bunch of hidden layers. Maybe simple, it just has one hidden layer. It's a shallow neural network. And then you're going to get the output at the output layer, right? Now, this neural network is not capable of processing a sequence. Everybody Everybody agrees? Because if I send it over a sequence, it processes the first entry, and then it goes for the second entry and processes it totally independently of the previous one, right? So I am good. It's not when it's processing I or am, it's not paying attention to I or good, right? It just processes am, right? This is not what you want. Now, what you can do, you can make a recurrence here. So you can define something called state, and you can build some recurrence inside this neural network. This is going to help you to memorize what is happening on your sequence, right? So this is the idea that we call it recurrent neural network. So basically, you get any neural network that you have, and then you build a recurrence into it, right? And it's going to have a state, and this state is going to get updated over time, okay? Now, let's take a look at one simple example. Let's say I have this shallow neural network. It has one input. It has one hidden layer, and then the output layer, right? And now the hidden layer, in this case, is going to be computed in this form, right? So hidden layer is going to look at the input data, multiply it with a bunch of weights when you have an MLP, right? And then after doing this, it's going to get unactivated features here, but you're going to add nonlinearity. You activate it, right? And then these are the features, the one which are going to compute you the output, right? So the output is going to focus on the features inside H, and then computes the output, right? Everybody's cool? Sure. This is a basic MLP. How I can make it recurrent? Well, I can simply think of this output at every single time to somehow, or this hidden state at every single time, to be fed back into the neural network as an extra input. It means that the second time that I'm processing, I'm not only looking at x at time 1, but I am looking at, x at time 2. I am looking into x at time 2 and the hidden state I had at time 1. The hidden layer, the features I computed at time 1. This means that a bit of information from time 1 is going to pass into time 2, right? And the output depends on both time 1 and time 2, right? Next time, when I want to compute the next output, I take the input at time 3, and I get whatever I computed, whatever I got at time 2, right? That one depends on time 2 and time 1, right? It's going to generate the output depending on time 3, time 2, and time 1, and so on, right? So you might initially somehow by adding a kind of recurrence here, like the one I showed here, we are somehow adding a sort of memory into this system, right? And it's statistically also valid to think like this. So how we can look at this? Well, we talked about this, that when we have a neural network, we can interpret this whole neural network to be a conditional distribution, right? So if y is, for instance, a softmax, right, output, this softmax output is basically computing that you had, right? That was the case, yes? So you give the input, and then you are computing the chance of every label happening, right? Everybody's cool? Yeah. So if you think about this, and basically we go ahead and maximize the likelihood. Now, what's going to happen if I add that recurrence connection? If I add this recurrence connection, this means that, for instance, at time t, same as time 2, when I want to compute the hidden state, or the features that I computed in the hidden layer, these features are computed from input at time 2, right, plus a weighted version of the hidden state at time 1. Make sense? Everybody's cool? And then I compute the output in this form, right, from hidden state at time 2, right? Now, if I want to write it down in terms of the distribution, what can I say? If at time 2 I am computing a softmax, okay, that softmax is giving me the probability distribution, right? That probability distribution is over the labels that I have, right? But what are the conditions? Well, obviously xt is going in, right? So it's given. What else is given? ht minus 1, right? ht minus 1 is also given to my neural network, right? So it means that neural network at time t is given by xt and the hidden state of the previous time, right? And is computing the conditional distribution. What is the chance of every single label, right? Now, if you think in this form, you could say that this h, if we start at time 1, say h does not exist at time 0, right? Time 2, it depends on time 1, right? So it's going to be h1 and x2, right? Now, h1 was computed by x1, right? So if all the computations are happening right, if h1 is carrying all information needed about x1, then I can replace this guy instead of h1 by x1, right? So I basically say that I am generating the label at time t with respect to input at time 1 and time 2 and time so on till time t, right? So at time 1, I am generating the label or computing the probability of the label with respect to the first input, right? At time 2, I am computing the distribution of the label with respect to first one and second one, right? At time 3, I'm computing the distribution with first input, second input, third input, and so on. Make sense? So these x1 to xt minus 1 are somehow getting encoded inside this hidden state. And because of this, every single time I am generating an output which is related to everything I've seen before, right? And now this guy is capable of processing a sequence, right? Because if the previous inputs are somehow correlated, this guy is going to somehow be able to capture it, right? Everybody's cool? Questions? So you got the idea? OK, so if you have any shallow neural network, hidden state, the output layer, and this is the input layer, the way that you can turn it into a RNN is quite simple. The only thing that you need is that in the first hidden layer that you have, right, in addition to looking into the input, you look at one object which is exactly like your features, right? So at time 1, you're looking to input at time 1 and the initial hidden state, which is a random thing you generate, right? But now you're going to compute h1, right? h1 is going to tell you what are the chances at time 1, right? For time 2, you're going to copy this h1 to the next time, right? So at time 2, the second input goes in. The features you computed up to this point come in. And then you compute second output, right? y2. And this guy is going to be is going to give you the distribution of the label at this time, given whatever you have seen, x1 and x2, right? And you can keep on going like this. I guess this here I wanted to put v2. Sorry, it's a typo, so it shouldn't be v1. It's just talking about the label at time 2. Yeah. Oh, I wanted to say that they are not aligned in general, but you forget about it. It's just v2 and vt here. Just forget about it. I don't want to explain those. I don't want to confuse you with the alignment problem. So here, what we are doing at every single time, say at time t minus 1, we already computed ht minus 1. We are going to pass it to the next time. We get the next input. And out of these two, we are going to compute a distribution, which is potentially talking about the distribution of the label at that time, given whatever you have had before. OK? Everybody's cool? Questions? OK, cool. So if you got no question, in general, you can build an RNN in this form, right? You don't necessarily need to have a shallow neural network. You could have a very deep neural network. And you have this deep neural network, but at some point, you're and every time, you're going to feed the previous one into your neural network, right? So you're going to keep this recursion inside your architecture. This is going to every time talk about the output given whatever you have seen up to that point, right? Make sense? OK. Now, RNN, as I said, is not very popular anymore. I mean, it never had been a popular or a good guy in his life, but because it's challenging to train, right? But at some point, when we didn't have transformers, we wanted to just process sequences, and then we had to deal with it. This is why we came up with the ideas of GRU and LSTM. Now, if you want to train it, you basically want to compute the gradient of your loss with respect to any weight that you have in this architecture, right? One thing, where are the weights located? H, right. H is the one which is carrying weights. I mean, Y itself could be also output of some weighted layer, right? But one thing that you should pay attention here is that the weight of all these yellow boxes are the same, right? Make sense? You pay attention to that? This is the important thing, right? If I change one of the weights in the hidden layer here, right? This is going to change at every time, right? Because my weights do not depend on time, right? So you don't think that I have one set of weights, second one, third one, till T1, right? It's not the case, right? At every time, when I change one of the weights, all the weights, whatever time is, are going to change, right? Because weights do not depend on time. Make sense? Now, let's think about training. And I don't want to open it up in details. I just want to give you the idea. Let's say that I want to train this neural network. What should I do? Well, my inputs, right? T different inputs, a sequence. The first guy goes in, right? The first output comes out. Hidden features pass. The second guy go in. The second output comes, and so on towards the end, right? Now you have y1, y2 to yt. What can you do with these outputs? Well, probably they are not the ones that you want. You want to train this neural network to give you that, right? What do? You compute loss and do gradient descent, right? How do you compute the loss? Let's think about a very simple example. Let's say that our problem is that you listen to a sentence and give one final argument about it, right? Sentiment analysis. You listen to the sentence, you process the whole text, right? At the very last time, at time t, you're going to say positive or negative. Was Yet at this time, you're going to have one output, your neural network, right? And you want it to be the same as the one you have in your data set, right? Which means that you have your data set, right? So this last guy, yt, is going to give you one loss, right? And now you need to be able to compute the gradient of this loss with respect to all weights you have in this neural network, right? What do you do then? What algorithm do you use if you want to compute the gradient? We did it before. What is it? Which algorithm computes the gradient in neural network? Backpropagation, right? You do backpropagation, right? Never forget the word backpropagation. Keep it in your heart. It's the only thing that makes the training happening, right? So this is backpropagation, right? You need to backpropagate. This means that you start here, you go one layer before, right? Compute the gradient of your loss with respect to all neurons in the output layer, right? Make sense? And then when you computed that one, then these are, by chain rule, connected to the gradient of the previous layer, right? Again, you go back and compute those gradients, and you keep on going, right? But here, the issue that is going to happen is that when I compute the gradient here, I get to this guy, right? So I can compute the gradient of r with respect to output. From the output, I get to the previous layer, right? But when I get here, right, the gradient with respect to this guy is the gradient with respect to h, the feature I compute at time t. It depends on the gradient of the input at that time and the gradient of the previous hidden feature, right? So I need to go one step back in time, right? Then I get to this guy, but this guy depends on the input at the previous time and the feature in the previous time, right? Make sense? So I need to go again back, right? And I keep going back. I keep going back till I get to the initial state, right? And after that, there is nothing to go back anymore, right? I stop. Make sense? Everybody's cool? You see the issue? If you want to do this, you can imagine if you write down the chain rule and formulate the backpropagation algorithm, it's going to be a recursive problem, right? And you're going to do recursion till the whole sequence is over, right? If you do that, you exactly end up with such a thing. This is what we call it backpropagation through time. I have not named it here. Yes, backpropagation through time, right? So this means that every single time that you want to compute the gradient, you need to go one time back, right? One step back in time, and know the gradient of the previous time, right? But the gradient of the previous time, again, depends on the gradient of the previous time and so on, right? So this is the algorithm. We call it backpropagation through time. And this guy could cause two kind of behaviors, extreme behaviors. When you have a very long sequence, it could either be vanishing gradient or exploding gradient. Now, what is vanishing gradient? Or maybe we start with the exploding gradient. Say you compute the gradient now, okay? And your gradient is some number, say 2, times the previous. And then you compute the previous gradient. It's again 2, right? So it's going to be 2 times the previous gradient, right? It's going again to be 2 times 2 times 2 previous gradient, right? You keep on going like this. So you're computing the previous gradients, right? And if most of them are larger than 1, as long as you get a bit long in time, the gradient is going to accumulate very, very large, right? And then this is going to potentially explode, meaning that it gets out of the floating accuracy of your computer. Your computer is going basically to treat it as an infinite, right? And this could harm your algorithm because you want to update. You had this weight. Now weight minus infinite is going to be infinite. Algorithm stops working, right? So this is a problem, exploding gradient, but it happens less frequent because we could, for instance, clip it, right? We could say if any gradient in this computation gets above something, stop. Don't update it. Just keep it that, right? It's a large value. It's OK, right? But the more serious problem we could have is the vanishing gradient. If you are going back, and most of the time, those gradients are smaller than 1, then they are going to multiply together, and eventually they become practically 0 for your computer, right? Now, here, one thing that you should pay attention to is that we do have also a vanishing gradient property in deep neural network. And there, really the behavior is that when you compute the gradient of the initial layers is always 0. They never get updated. And since they never get updated, they cannot extract good features. And because of that, the whole learning after that is getting trouble. But here, the vanishing gradient is not showing up in that form. So it's not literally making the gradient 0. It's making time is not small, right? When I am here at time, I compute my gradient, and my gradient is going to depend on the previous time, and so on, right? Each time, when you write down the backpropagation through time, each time you are going to get the last gradient plus last gradient times something else, right? And it keeps going like a multiplication like this, okay? And this means that at the end of the day, the gradient that you find depends on whatever you have seen recently. And it's not going to depend on the very long time ago. If you want to talk about it statistically, this means that the hidden state that you see in one time It captures the features of the previous recent entries inside your sequence, but it starts to forget whatever was happening at the beginning, right? Because it's not super powerful. It does not have infinite memory. Make sense? So this is you could do nothing about this vanishing gradient, and this is why we always say that RNN has a limited memory, right? Even though theoretically it could go forever time, in practice it cannot go beyond horizon, and that horizon is that time window is going to specify how well the memory of the RNN could work. Everybody's cool? Questions? Okay. So if you got now a question, some classical remedies for that, clipping, as I told you, this is a solution for exploding gradient. There is some idea called truncated backpropagation through time, which you start with your sequence. You do not go forever. So you stop at some point, you update, and then you keep on going, right? Since you are not stepping up more than the memory you have, each time you can process to your memory, right? And this is going to help you improve the training of the neural network. Also, you could use the gated architectures. Gated architectures are the one which made RNN quite practical. So you probably have heard of LSTM, right? Long short-term memory, right? Or GRU, gated recurrent unit. They are actually gated architectures. And they somehow use the idea of gating to expand the memory for larger window. Everybody's cool? Question? No question? OK. Now, I am going to just show you here the famous recurrent architectures. This is the basic one that we already talked about. I'm going to show you also LSTM and GRU. But I do not expect you to get all the details, because they need a bit of more details. I mean, you really need to write the backpropagation through time and exactly feel where gating makes more sense. I just want you to have it seen, right? Just in case that you wanted to use it at some point. OK, so this is the basic RNN that we talked about up to this point. So what we have here is a kind of junction. So you get the hidden state in the previous time. You get your input at the current time. Every single one goes on one line. And these lines carry weights, right? So they have their own weight. So it means that the first line is going to multiply x with a bunch of weights. The second line is going to multiply the hidden state with its own weights, right? It adds them up, and then it's going to activate them. And a typical activation that we use in recurrent networks is tanh. The reason is that it's going to somehow reduce the impact of vanishing gradient. Okay? This tanh has this nice property that when you multiply it too much, around 0, too much, it's going to vanish slower as compared to many other. This is going to give you the next hidden state, right? And this is what we call it a recurrent unit, right? Because the unit needs to see whatever had been done before, the new input, and it can give you one output, right? Now, if you want to use, for instance, input to classify something at time t, what do? What would you do with ht if you want to classify whatever you have seen up to time? You can get ht. You can multiply with a bunch of weights, right? Then you will compute a softmax, right? Make sense? Everybody sees what I'm talking about? Yeah? So this ht has information, somehow encoding information up to time t, right? If you want to classify anything at time t, you can get ht, compute a softmax output out. ht depends on everything before, then that softmax is going to compute you what you want, right? long as you train everything together. So this is the basic RNN. This guy is the GRU, the gated recurrent unit. And this one might look a bit complicated because it has gates. What are the gates? I'm going to explain shortly. Here you have two different gates. Wherever you see a sigmoid, this is a gate. Okay? So a gate is going to get whatever comes into it, and then it computes a weighted sigmoid activation is going to make the output to be 0. It's 1, the gate is completely open. When here we have two gates. One of them is the reset gate. The other one is the update gate. Okay? Now, let's see how does these two gates work and how do we get the hidden state updated at time t. Well, let's say I have the input, okay? And I have whatever memory I had from before, right? I get the input, I get the memory from input. I compute some weighted sum of them, right? So input multiply with some weight, hidden state multiply with some other weight. They add up together. I get the update, this input, right? I'm going to pass it through a sigmoid, right? When I pass it through a sigmoid, it's going to be something between 0 and 1, right? Now, this guy is what I call it the update gate, and then I compute the same thing. I call it reset gate, okay? Now, if I want to compute the output, first I get this hidden state, and I multiply the reset gate with that previous memory, previous features I computed, right? If I set reset gate to be 0, if I close that gate, what's going to happen? Exactly. So the previous state is going to get forgotten, right? You just talk based on the new state, right? Make sense? I mean, sorry, new input. Make sense? So when reset gate is closed, everything going to get reset, right? Because the previous ones are getting forgotten, right? If reset gate is completely open, then the previous guy is going to show up, right? And then your new state is going to depend on the previous ones, right? If you want to think intuitively, let's say that you were processing a text, right? You start from the text with the first sentence, you go on, the sentence, right? And then you go for the next word, it starts the next sentence, right? And that one, you don't really need anything from the previous sentence because that is totally independent, for instance, right? If the reset gate at that point gets to start over by the new. Okay. What about the update gate? The update gate is going to get multiplied with whatever you computed. So this thing that you are computing is either totally depending on this new input or is depending on the new input and the previous ones, depending on the reset gate, right? But at the end of the day, this is going to represent your new features, right? This HTL. Now, you are going to multiply this update gate with the new features you computed, right? And you also multiply 1 minus this guy, same update gate, 1 minus that, with the previous hidden state, right? Now, let's first think that the update gate is 0. It's closed. What's going to happen? What would be the next hidden state? This update gate is totally closed. If I set it to be 0, what's going to be HT? I will. It's an article in the sentence, right? I was processing the word the, right? And the is not carrying any information as long as I'm concerned about the concept of the sentence, right? Make sense? Now, if I keep this hidden update gate totally open, so I set it to be 1, what's going to happen? What would be HT? If update gate is 1, what would be HT? If update gate is 1, then this 1 minus update gate is 0, right? So 0 multiplied by this one, this guy is going to cancel out, HT minus 1, right? So HT is going to be 1 times H tilde, right? So HT is going to be exactly H tilde, right? And H tilde was computed from my input, right? So when the update gate is totally open, I'm going to rely totally on the new features I extracted from the new sample, right? So I let it to be updated, right? And if it's something in between, then, well, I let it update halfway, right? Make sense? Everybody's cool? Questions? So that was GRU, and we have the same form of architecture. We call it LSTM, long short-term memory. And LSTM is, again, a gated architecture, but it has a bunch of more gates. Okay? And I guess, like those of you who had deep learning course, you have heard of me telling you this story. But this is one of the interesting stories in computational learning. This guy was actually invented long before people got back to RNN and started to understand gating. Like it was, I guess Schmidhuber, he was the one who invented it. He was a master's student at TU Munich, and he did his master thesis. He wanted to do sequence processing. He came up with this idea. I guess he didn't call it even gating. Like by adding these modules, you can somehow expand the memory. And then he defended his master thesis. He did his PhD. He became a professor. He had his own PhD students, and so on and so on. People at some point got confident that we can get back to sequence processing, like when the neural network started to get popular again. And then at some point, they were struggling with RNN for another time. And then his former supervisor, the one who supervised him during master, he said, like, well, we're trying so hard. Come on, look at this. My master student did it a long time ago. And they went on and they said, oh, really working. Actually, it's making the training stable. It's making the memory longer. And then they tried to understand why this is happening. And then they came up with the fact that it's using gating, right? So they build it as a simplified to understand, to make sure whether this is real or not, right? So not call it gating at all, and this was left for a good amount of time. Anyways, so this one has more gates, so it has one thing which we call it forget gate. Obviously, you can guess this is going to make us forget the previous, something like the reset gate we had in GRU. We have the input gate, which is going to somehow control whether the input is getting in or not. So you can somehow gauge the input as well. And you have also an output gate, which is going to gauge the output of your neural network, how much of this you want to pass to the next time. Here we have two different states. So we have CT and HT. Both of them together are basically the hidden features, the hidden state that we have in this recurrent module. But we separate them because we compute the output separate only from HT. And CT is somehow kept in the architecture as a kind of self-memory. And if you want to think about what you're doing, here you basically, again, get these two guys and do the basic, activated, weighted activation of them. Then you're going to get the input gate. Input gate is going to control how much of this feature you computed here is going to pass. And also you have a forget gate, which is going to get multiplied with the previous state, right? If the gate is closed, the previous state, that everything you compute is based on your new features, right? If the gate is open, then you're going to get that one as well, and that guy is going to add up to your new features, right? Same thing for the input gate, right? If input is closed, none of the new features you computed are going to pass. If it's open, then the whole features are going to pass. Make sense? You get this one? This is going to be your new state, right? The new kind of features you have in this recurrent network. But you have the last part, which says, OK, I got this computation that I had here, right? And out of this, I'm going to compute one, which is the output, right? So I'm going to again look at my input and previous memory, and I compute one gate out of it, right? That gate is going to decide how much of whatever I have found is going to pass to the output. Again, if I set this output gate to be completely 0, I close it, then nothing is going to pass. New output is nothing, right? I close everything, right? If I keep it completely open, then I'm going to pass everything that I computed. Yes? Yes?
How is the value for the gate determined? When is it?
I didn't get the question.
Like the gates. How do you determine if it's open or closed?
Oh, this is computed by the weights you have. So here, this gate, you get your input. It gets multiplied with its own weight. The previous memory features get multiplied with another weights. Okay? They're going to add up, and then they get activated by sigmoid. Those weights decide whether this is open or closed, right? And if you pass it through a lot of data, then it's going to get trained. So for instance, if you see here, maybe here it would be better. I don't know. Or maybe in this architecture it was better. I don't know. Okay. Yeah, let me just explain. But let's say this guy is the article, THE, right? And then you do this computation here, so you get a bunch of features, right? But if your neural network has seen a lot of THE, the, in the sentence, at some point you're going to get the feeling when XT is the, then essentially I don't really need to update anything, right? There is no new information added, right? If that is the case, hopefully this, for example, input gate is going to be 0, right? And then this forget gate is going to be 1, and then this guy is going to pass, right? Means that the memory does not need any update because it's a kind of article carrying no specific meaning for that. Make sense? Yes?
The value of gate, is it between 0 and 1?
0, yes, sigmoid. The activation you use always is sigmoid, right? And that one is always between 0 and 1. Questions? Yeah.
Is there a state in the middle of the state, like
Yes. I mean, in practice, you get, those ways are going to give you somewhere between 0 and 1. But you could say, like, depending on the meaning of the word you have, it could be more towards 0 or 1.
And like, how does the affected by this, it's like semi-state?
If it's not going to impact, its corresponding weight is going to somehow train to be 0, right? But if it's, you might wonder why this should show up here. Well, it again depends on the fact that, for instance, you have the whole information before, and then the new input that you get is a final period in the sentence, right? Now, if you start with the next word in the sentence, you first need to make sure, like the previous sentence, conceptually is not that. Then you can maybe make the forget gate, and then you kill everything. So you need to take a look at whatever you have extracted up to this point to make sure, like, whether you really want to forget it or not, right? I mean, in practice, you really, I mean, sigmoid can never be absolutely 0 or absolutely 1. This means that a tiny bit is going to pass always, right? But probably it's going to get small enough that most of the information are not preserved anymore. Make sense? Questions? No question? Okay, cool. If you got no question, so gating, this idea of gating was quite helpful. So this could control the vanishing gradient. This could cause better training. And this was one of the first serious kind of sequence processors that we have. If you still have a simple task, sequence processing, like probably it was a kind of common project many people do, price prediction, right? You look at prices and volumes of stock, and you want to predict what is the price tomorrow, right? Or weather forecast, right? For those ones, you can simply train in LSTM. It's going to work perfectly because the amount of information available in that sequence is not too much, such that the model really needs too much of complication. So LSTM with just one recurrent unit, you don't need to even make it that deep, is going to work fine. But if you get a more serious task, language modeling, this is not good. Okay, so yeah. Now, when people started using LSTM and they saw some results, they got a bit interested to go beyond basic tasks, like price prediction or something. They started to think like, okay, maybe we can use it to do translation, right? We have one LSTM, which is capable of talking. We have one other LSTM, which is capable of taking a sequence in and processing it into one concept, right? Context. So we can use these two LSTMs, right? One of them, the sentence in French, it's going to extract the context. The other one, take this context and start to talk in English, right? And it's going to give us the translation. But it was not as easy as price prediction to train this one, right? The very, very first version of language models, they were actually LSTM. So you can train an LSTM to become a language model, actually, to talk for you. But that could just talk for a few words, a very short sentence. When it gets longer, it starts to just give you redundant words because it somehow starts to forget it before. Okay. Happy today is very good, so on. Like the rest of the text is not depending on the previous one. It's like someone who just wants to say something in English, right? It doesn't want to transfer any information, serious information. So, yes, so this RNN, as I said, it has, at the end of the day, the RNN, even if it is LSTM, is going to have a limited memory, and people started to try somehow expanding this memory. They said, like, is there a way that we can make this memory much longer? Like, I can generate one text of length, I don't know, 10,000 words, and I am talking, the model network can remember what was this sentence about at the first place, right? So the idea of attention mechanism got developed. So this was somehow adding connection to every single word inside your sentence. And by adding this attention, they saw that they can actually significantly boost the idea of sequence processing. So this is around 2015, 2016, when attention was somehow being used. And people got very excited, like we can do attention, so we can process, but it's still that we're using LSTM. Up to 2017, when this famous paper came out, attention is all you need, right? And then this paper said that essentially you can forget about all of those time connections. You can just do everything solely based on attention, right? It's a bit of mess. The calculation there is a bit messy. And it's basically just a computation. It's not like a very serious statistical idea, but it's super efficient. You can do parallel processing. You can get direct connection to every single token in the sequence. And because of that, every time that you are generating something, you actually can take into account everything you have said before, right? And this is when they call the architecture to be transformer. If you read the paper has even typos. It has like basic syntax mistakes because the one who wrote it, they never expected it to just boom out like this, right? But people started to get the idea and implement it, and they saw that, wow, it's getting implemented easily. It's very efficient in terms of computation, and it can actually resolve whatever we had before. And this is when the transformers started to get out. GPT, famous one, right? Pre-trained transformer, which you can use it for anything nowadays, right? Everybody's cool? Questions? OK, if you got no question, you can take a look at Goodfellow textbook, the deep learning, if you are interested to know about RNN. In deep learning course, we actually cover both of them, RNN and transformers, attention in detail. So if you want to see a bit of math and calculus detail, you can take a look there. And there is also one other course, Creative Applications of NLP. We have it fall semesters here at ECE. Professor Rose is teaching it, and there you have you work with natural language processing tasks, and transformer is the basic architecture that you always use. So I guess the lecture will start with just transformers immediately. Questions? OK, so now let's start with the sequence model, and then when you start with this one, you can start doing crazy stuff, which ends up with these different kinds of generative models we have. So one first question that people were, for a very, very long time, interested on was that, can we make one model which generates a coherent text? And what do I mean by a coherent text? It means that it can just simply keep talking. And then when it talks, when it gives you every single word in the sentence, is it syntactically correct and is also carrying meaning, right? So it doesn't say like, I am potato, or I don't know, I are good, because they are either syntactically wrong or it doesn't have meaning, right? Well, if you think about the learning problem, you essentially have a sort of supervised learning problem here, because you have a sentence, right? When you have a sentence, you can take it as a sample, and you can make your neural network to look at whatever had been up to this point, then give me the next token, the next word, right? So you can always do it, so you can take each sentence to be one sequence, and every single next word is going to be the label of the previous word inside the sequence, right? So I am happy, right? For I, the label is am, right? For am is happy. For happy is end of the sentence, right? Make sense? So this is a kind of supervised learning problem. And people, once they got a bit of self-confidence with RNNs, LSTM indeed, they started to say that, OK, maybe we can try to train this architecture to talk, right? Meaning that they just go ahead and download whatever text they could. Nowadays, when you think about the large language models, they essentially download what they call the main body of internet, right? So they take whatever text they can get, they download it from internet, they clean it up by getting rid of HTML preambles and other things. Then there are a bunch of texts which are nonsense, a bunch of texts which are dangerous, or a bunch of texts which are immoral, so you need to filter them out. And then you remain with some safe, correct sentences in different languages. Now you start sample one sentence. It is one sample, right? And you try to make your neural network to give the next token, right? Next word. So if you want to do the training, obviously you can use cross-entropy, because you can make, your neural network would always choose or classify the next word among all possible words it can say, right? And then you want it to have the high probability for the right word, right? So yeah, for example, if you use LSTM or any recurrent neural network, the first guy goes inside the recurrent unit, the first word. Then you're going to get an output, and then you make this output to look like the first word, the second word inside the sentence. Then you're going to get this one, and you give it back to the sentence, to the neural network, right? And this one is going to give you the second, the next word, the next output, sorry, which you want to be the third word inside the sentence, all towards the end. Now, if you assume that you can do the training well, then you can simply use this architecture to talk for you, right? You put the first word, right? Your first word could be one part of the sentence, right? For example, I. You put it as the first word. Or you might just randomly give an input to it, right? Or maybe you just give it a start, right? One specific token, the start, right? Then it's going to take this one and give you the first output, right? The first output is the first token inside, the first word inside this sentence, right? It's I, right? You get this I, and you give it back to your recurrent unit, right? You're going to look at I. Well, nothing had been before I. The first word was I. Now, the next word is going to be am, right? I am going to give am to this recurrent unit again, right? And then you're going to look at the memory, say, I already said I, now am, so the next one is happy, right? End of the sentence, sentence is over, right? Make sense? So if everything works perfectly fine, then this guy is going to work, right? And it's capable of talking, right? This was a kind of dream come true for many people, because for a very long time, people were trying to understand how we can talk. Is it possible that we build one machine which is also able to talk? So yeah, that was the idea. And this is what we call it the language model, right? So statistically talking about it, a language model is what we essentially sampling from the language distribution every time that you prompt from it. ChatGPT is a language model. I don't know, Grok, all of them are language model. And the job that they do is that they are able to complete one sentence, one natural language sequence. Right? So ChatGPT that you have, it does not learn separately how to, for instance, answer your weird questions. It does not learn any of that. The only thing that it learns during the training is that any sentence given to it, it's going to complete it, right? But once you can make this, you can do whatever you want, right? Statistically. Now, you can write it down a bit mathematically, and you understand that everything's going to work out statistically. But you can also guess intuitively that this is correct. If I have one machine that is able to complete a sentence, right? If I want to ask a question from it, for example, what is the color of sun, right? I don't need to ask what is the color of sun, because it does not know how to answer. It did not get trained to that, right? I would say, OK, the color of sun is, and then it's going to complete the sentence, right? Is, what is the color of sun? It's not yellow, obviously, right? It's not yellow. Yeah, definitely. It's white, I guess, yeah. I mean, it doesn't have really, you cannot define color for it, but yes, white, because it includes all spectrums, right? Is whatever, right? End of sentence. Make sense? So this job, completing a sentence, that's all you need when you're dealing with a natural language sequence, right? And you can use it for different things. As I said, for text generation. Text generation makes sense, right? You just start your language model and start to sample, right? I am happy and good today. End of sentence, right? Again, you randomly sample from it, right? It says, he is bored, right? You again sample from it. Tomorrow is raining. Tomorrow will rain, right? Things like this, right? It's going to give you right sentences whenever you do that. Auto-captioning, again, you can do it using a kind of the idea of sequence-to-sequence modeling. So you get your image, you process it, you get a bunch of features. You give those features to this language model, and say start, right? It's going to look at those features and starts talking. This is image. It can talk, right? Once it can talk, it can finish the job for you, right? So you can do auto-captioning. Translation is the same thing. Again, you listen to a sentence in one language. You extract the notion, right? Somebody says something in another language, right? Then it says it's going to capture the features out of it by encoding it, right? First it says, you say by a sequence processor, you're going to get this idea. This vector is containing the whole information inside this sentence, which says the guy who is talking is happy, is a single person, and is talking in the present tense. And then you're going to give it into a language model. And the language model is going to say it in English, right? I am happy. Present tense, single person, happiness, right? So you can do translator with them, and also reasoning algorithm, obviously. You can do it as well, right? Because if the language model wants to generate a sequence, a sentence, right, it needs to understand whatever has happened before, right? So at any time, if you want to reason, right, so you're going to get that context at that point, right? And this is going to be what you need for your reasoning. But, well, it needs a very long further processes, right? So one thing that I have mentioned here, NLP, natural language processing. Well, language models usually work on natural languages, right? And by natural language, I do not mean English, simply just language spoken by human being. Like programming language is also a natural language, right? Because it has syntax. You cannot write every sample things next to each other, right? Yeah, this is the main, language model is the main object, main module in natural language processing. Because anything you want to do there, at the end of the day, you can break it down into sequence of problems being solved by language models. Everybody's cool? Questions? OK. Now, one thing that is interesting to look at is statistical viewpoint on the language model. So what is language model doing? At every single time is giving you the next word, right? The next token in the sequence. By the way, do you know what is token, right? Token, if you have a sentence, you can break it down into small pieces, right? Those pieces could be one word, could be half of the word, or whatever, right? They are what we call a token. Now, you're going to get the probability of the next token given whatever token you had up to this point, right? The sentence was going on, I am happy, and now we want to just give the next token, right? So what you are doing, you're computing the probability of the next word, next token, given everything before, right? For instance, let me just give you one example. The sentence is, he does not see what she, this is what the language model wants to complete, right? If the language model is really working fine, then it should give you a probability distribution at the output, right? All possible tokens, like thereafter she can see any word that you can think of, right? But what are the chances, right? If this is really a language model being trained properly, so it should never put you C here, right? Because what she see is grammatically wrong, right? If it's a native English speaker, never says C, right? Or for example, what she am should not happen, right? So these probabilities are going to be small. They are going to be 0, practically, right? Whereas you could have what she sees, right? Or what she can see, right? Or what she have seen, right? So all of those other possible tokens, which are grammatically and meaningfully right, they can see it here, right? And your language model supposedly is computing that distribution for you. Make sense? Yes? So the ideal language model really is 0 here, is non-zero here, right? And now, is it C's, for example? Well, you can go and look at the text, right? The whole text being generated by a human being, right? How much fraction of time after this phrase you see C's, right? The language model should give you roughly that probability, right? If over all text available on this universe, C's has happened 20% of the time, then this probability should be 0.2. Make sense? Everybody sees that? So this is what the language model is doing, right? Every time it's sampling from this, right? So it's like a machine, random machine, with this distribution, right? You just push the button, one of the possible words come out, right? You put that guy there, now the whole text again go inside this machine. It gets tuned to the new distribution. You press the button, the next word drops out, right? And it goes on completing the sentence, right? Everybody's cool, yeah? So that was the idea, language or the ideal language model. And then the language model that we implement in practice is actually trying to estimate this true distribution, which we cannot obviously see, or we do not have access to it easily. It wants to somehow approximate it from the data, right? So what it wants to do, it looks at your data, right? And then it puts one neural network. That neural network output looks like a distribution, right? And then it uses RNN, it uses transformer, whatever sequence processor it is, right? To somehow generate one distribution based on whatever it has seen, right? And it tries to match this distribution to the true data distribution. Everybody's cool? Now, first thing first. How can I make this model? How can I make the output of my neural network to look like a distribution? Is it a complicated thing? No. What? Softmax? Great, right? So you see it, right? So I can put one neural network, and this neural network takes whatever had been, right? And then it just computes, and one softmax is the probability of the next token, right? Everybody's cool, yeah? Now, this is the first thing. The second thing, how can I match this one to my data distribution? Any idea? If I have samples of one distribution and I want to learn that distribution, what is the trick? What is the learning algorithm? I mean, it could be Bernoulli or whatever distribution, but you have only samples. Maximum likelihood, right? You're going to do maximum likelihood, right? So you're going to compute the likelihood of the parameters in your model, given the data that you have, right? And you try to maximize it, right? Make sense?